So good afternoon, everyone, and welcome to our presentation on our autonomous juggling robot. My name is Krish Desai.
I'm Shana Chen.
I'm Aanya Gupta.
My name is Olivia.
And I'm Barsa.
So today we're going to first talk about the history and impact of juggling robots, followed by a brief discussion on different types of juggling patterns. We're then going to explore our design for this project, followed by the methodology and procedure we followed, and the data and results we were able to pull from that. So juggling is an intricate art, and it requires both dexterity and agility. However, there's also a third component that not many people might know about, and that's human instinct. See, studies have shown that when human beings juggle, they make and execute decisions faster than the measured human reaction time. And what this means is that there's a feedback loop of human instinct, and scientists aren't really 100% sure why this occurs, which has motivated the development of juggling systems. A juggling robot allows scientists to study a similar feedback loop without having to deal with the confounding variables that arise in human studies. Juggling robots signify an advance not only in robotics, but also in our potential understanding of the human brain. And that has huge potential improvements in fields such as biochemistry, medicine, and more.
So there are many different juggling patterns. The most common pattern is a 3-ball cascade, probably the one you're most familiar with. And however, there are other juggling patterns called side swaps. And side swaps are where each ball is in the air for varying time intervals. So over here is a 5-3-1 side swap, and the numbers correspond to how long each ball is in the air for. So the highest ball is a 5 because it is in the air for 5 time intervals or beats before it is caught again, similar with the 3 as the middle ball and the 1 as the lowest ball. In the center, there's a ladder diagram, and ladder diagrams they help jugglers determine how long each ball is in the air for, as well as which hand is doing the catching and the throwing. So the bars represent the left and the right hands, and the hash marks represent the time intervals or beats, and then the slanted rungs represent the paths that each ball takes. So as I was talking about before with the 5-3-1 side swap, the number 5 is above the first time interval, meaning that it's thrown first. Similarly, 3 is above the second hash mark, meaning it's thrown second, and the 1 ball, which is the lowest ball, is being thrown last.
So the main goal of our project was to build an autonomous robot that can juggle up to 5 balls in a cascade or perform a side swap up to beat 7 reliably and consistently. As we mentioned previously, this would be the first step in studying the connection between the human brain and juggling.
So we developed a project design that involved linear actuators. And linear actuators are similar to electronic pistons in that they convert rotational motion from a gear into linear motion using a rack, which is a straight part with gear teeth. And linear actuators will help us propel the ball upwards along a backboard along a much more predictable vector. And in addition, they can extend, retract, and change angle very quickly, making the angles very precise and much easier to program the ball's trajectory. So linear actuators will help us accomplish the task of juggling in cascades and side swaps because they can be programmed to have very exact angles and help us predict the ball's trajectory.
So we used Autodesk Inventor, a computer-aided design software, to design our linear actuators. We realized that commercially bought linear actuators are too slow to propel the marble to the height we needed to go. So we decided to 3D model and 3D print our own. The only part that we bought was the 775 Pro DC motor. So we had to make sure that the gear, the bracket, and the rack all were dimensioned properly to align with this. And in order to do that, we downloaded separate part files for the gear, the rack, and the bracket, and then modified them to fit around the motor. So first we had the gear, which fit around the motor and also interlocked with the rack, and it was able to convert rotational motion into linear motion. And then the rack acted as our linear actuator, and the bracket held all of our pieces together. So the marble would go on this end of the linear actuator, so that when the motor is turned on, it would drive the gear to then propel the linear actuator forward. And lastly, we also 3D modeled a funnel. This would help the marble stay on its path on its way up and also provide a range for it to be caught in when it was coming back down. And we designed this part from scratch and also designed it to lay against the back of
board. Okay, so in order to build the actual robot, the first thing that we did was drill 2 holes into the back of a 2x4 foot laminated plywood board located here and here. And the purpose of drilling these holes was to mount the servo motors to the board. So servo motors are motors that can be programmed to turn to exact angles. And the ones that we purchased are high torque, meaning that they're able to rotate heavy objects, which is important in our project. And pictured here is the servo motors mounted to the back of the board using screws and clamps. Then on the front of the board, we mounted the 775 Pro motor to the 3D printed bracket, which houses all the 3D printed parts. Next, we attached the funnel to the bracket using epoxy glue. And then we attached the brackets to the servo motors on the front of the board, which allows them to turn when the servo motors are turned on, and we can fire at whatever angle and catch at whatever angle we decide to. Next, we raised the angle of the board to 15 degrees by adding a piece of wood in the back. We mounted the Arduino and breadboard to the front of the board. And finally, we added blocks of wood behind the rack. And the purpose of this was to standardize how far the rack can retract. Therefore, we can launch the marble at the same speed every time.
Okay, so this is the circuit that makes the whole robot operate. Right there is the Arduino Uno microcontroller, which is essentially a small computer that you can program to control electronic parts. On the other side is a 9-volt power supply, which gives us all the power we need to launch our objects at high speeds. Then in the middle, you can see 4 different motors, 2 of which are servos, which you can essentially set to any angle you'd like. That's how we choose our trajectory. Then the other 2 are DC motors, which basically turn back and forth in order to extend and launch the actuator, and that's how we fire the ball. Then that small rectangle in the middle is an L293 motor driver, which basically varies the current going to each of those DC motors in order to get them launching at different speeds. And this is the flow chart for how the code works in order to actually perform juggling. In this case, this is a 3-1 site swap, so one of the balls is going to go at a height of 1, then the other one is going to go about 3 times higher. So the way this works is, here my arms are going to be the actuators. At first, both pull back in order to be in launching position. Then the one on the left is going to raise because that's going to launch at a 3, and the other one is going to go to a position to launch at a 1. Then the loop starts, so this part is going to repeat over and over. This one is going to fire by extending and retracting. And then while that's in the air, it needs a little bit of delay. So then once the delay is over, this one pulls back and fired, and now they're both in the air. So then we add a longer delay so that they both end up getting caught in the opposite funnels, and the cycle repeats.
So we generated this data table using kinematics equations that we derived. We determined the initial velocity and the launch angle of each marble given the site swap height that we want them to achieve. So we hard-coded these values into the Arduino, and essentially if we want to program a site swap, or we put in the height that we want it to go to, and then it will take the velocities and angles associated with that site swap height and send them to the motors.
So here we performed a 2-prop z-test, one of the statistical analyses we performed. This test was designed to check the consistency of both the motors. So for this test, we set the motors both at a constant angle with the same speed, and we determined the proportion of times where the motor would make a successful catch. And for a base assumption, we assumed that the motors would both be equal, and so those proportions would be equal. However, through testing, we found that one motor made a successful catch 70% of the time, and the other motor made a successful catch 20% of the time. So if you look at the equation at the bottom, the probability of that occurring when both the motors are consistent with each other is 5 times 10 to the negative 7, which is obviously extremely low. In fact, it is so low that it provides us with convincing evidence to say that the motors are not consistent towards each other. The second statistical analysis we performed was for a T interval. Here, using a 1-ball cascade, so that's just one ball bouncing back and forth, we counted the number of times that a successful catch was made. Using a T interval, we can determine that the true population average for the number of catches the robot can perform before failing is between 1.2 catches and 2.7 catches, which is, of course, low. We would prefer it to make more than 2 catches on average. So, our results overall, the robot was able to rotate the actuators to specific angles to fire the marbles, and it was able to catch them as well. So it did simulate juggling, but just not to the extent that we really wanted it to. The little animation that played on the bottom here was made in MATLAB. It's a simulation designed to show how a 531 site swap would work, and the graph on the top, also made in MATLAB, shows the trajectories of the ball at each possible site swap height 1 through 7.
This is a
just a video of
successful
us
one-ball cascade. Then this is a successful 3-1 site swap.
So in order to further our robot, a closed loop system could have been used instead of an open loop system. The open loop system that we are currently using basically puts in an input to produce a predetermined output, but a closed loop system would implement computer vision and a camera to track the trajectory of the ball, allowing the robot to adjust its launch vector to account for any discrepancies. And it would also allow us to integrate machine learning algorithms, making our robot much more reliable and consistent. By having a more accurate and reliable robot, then we could also study the connection between the human brain and juggling in a more accurate fashion.
So once again, the goal of our project was to create an autonomous robot that can juggle up to 5 balls and perform site swaps. In the end, we were able to build a fully functioning robot. However, it could only juggle 1 ball and perform a 3-1 site swap. So we did not accomplish our goal completely. Therefore, further testing will be required to accomplish the goal. So the overall goal of this project was to eventually be able to study the human brain through juggling movements. And in order to achieve this, first a closed loop robot will need to be made in order to better mimic the human brain and study this movement. However, in order to accomplish this, first an open loop robot would need to be created, which is what we were able to accomplish. And although it wasn't able to perform all the patterns that we were hoping it could, it still functions well, and we have made progress in this field. So therefore, any research that continues on by studying juggling movements from our robot could have discoveries that could imply new understandings of the human brain and the human body.
Okay, now we'd like to acknowledge and thank everybody who helped us with this project, including Mary Pat Reiter, Matthew VanDusen-Gross, Ryan Wu, Professors Kralius and Shinbrat, Shravan Venkatesan, Helen Sages, Michael Higgins, Dean John Patrick Antoine, Rutgers University, the Rutgers School of Engineering, Lockheed Martin, the New Jersey Governors School of Engineering and Technology Alumni Association, and the New Jersey Space Grant Consortium. Any questions?
Do you use a mathematical equation to determine the angles, or is it trial and error?
In theory, it's trial and error, but of course, any physics isn't accurate to the real world. So essentially, we set it to that originally, and then we trial and error to iron out the errors.
Did you think of using a stepping motor for your launch motor?
So,
extremely accurate and have very high resolution.
So a stepping motor was one of the motors we considered in the original project design, where we'd have like a rotating cup system that would fire balls upwards. However, given that we changed the project design to use linear actuators, we felt that a DC motor might be better because it doesn't have to be super accurate given the fail-safe stops that we put in for the rack and pinion.
Then how about using a linear motor?
So
It's simple to use.
the linear actuators that we found online were too slow for the speeds that we wanted to achieve, which is why we tried to build our own.
Yes.
Okay, so sensors are a mark of a closed loop system, and that's one of the potential improvements that we would like to make in the future. But for now, we have an open loop system that doesn't use sensors.